Okay, welcome everybody to the first paper session of this morning. So the theme of this session is network forensics, and we will have two presentations. The first presentation is from Stewart, Sentanoe and Hans Reiser. And the title of this paper is SSHKex, Leveraging Virtual Machine Introspection for Extracting SSH Keys and Decrypting SSH Network Traffic. So I will hand over now to Stewart.
For introduction, my name is Stewart, and I'm a PhD student in the University of Basel, Germany. So today I want to share with you my ongoing work with my professor Reiser in the title of SSHKex, which is meaning SSH extraction, and then leveraging machine-to-machine extraction for extracting SSH key and decrypting the network. So this topic will be in conjunction with forensic and forensic at the same time. Okay. So this the outline of talk today. I will briefly give you some introduction and some background, so like common knowledge here and some related works to see what's different in previous work, my work, and then the design of SSHKex itself, some results, evaluation, and if time permits, I will show you some video demo, and of course then I will conclude the talk. Okay. Let's start with the introduction. So I believe that all of you know already what is a secure shell or SSH. So basically it's a way that you can communicate with the remote server, you can do stuff on it, and encrypt your network packet, which is actually encrypted privacy, which is nice. But as you know that SSH can be an entry or point of attack, especially if they use the weak credential. So yesterday there was one talk talking about the password, and there's so many people that are still using with password like admin 1456, 1444, and so on and so forth. So how there are some approaches that are available how you monitor each traffic or monitoring. First you will do the active man in the middle. Second you can do agent-based monitoring. And lastly, you can do some kind of binary manipulation. I will explain this more in the next slide. So for myself, the requirements that I want to achieve for designing this SSHKex first is stealthiness, so it will not be easy to detect. Next is preservation, which means I want to avoid any modification of the target system. And I want to achieve also evidence integrity, so it's a variable integrity, so nothing changes, that it's real, that it's come from those VM or those traffic that I can try to prove. So I introduce SSHKex, which is all machine introspection based. So for the current key extraction approach is active man in the middle approach, which is first easy to deploy. But of course, it's easy to detect because the host key will change. So if you try to connect to the server the second time, some warning they say, okay, host key changed, so you want to proceed or not. So you know that something changed there. Next is agent-based monitoring. Again, easy to deploy. The problem is require access to the server to install the agent base. Lastly is the binary manipulation. It requires you to learn the source code, and then you modify the binary somehow that it locks any traffic connection or authentication log, but you need to of course plan modify binary for the server. Again, require access to the server. So that's some introduction. Now we do background a bit. So again, I will not do much in high level perspective what is SSH, but what is important for the research is basically exchange session keys, SSH itself. So the key exchange is in RFC 4053. It's based on Diffie-Hellman exchange. At the end, it will put the key with the K and hash value with H. So the session key will be derived from the exchange, producing 6 keys. First is A, call it for the initial factor client server. The key B is the initial factor for the server client. The key C will be the encryption key from the client to the server. The key D will be the encryption key from the server to client. And if you enable the integrity check, then you will have E, which is the integrity key for the client to the server, and key F from the server to client. So basically it will use symmetry, but from server to client, it will have different keys. Okay. So what's important for this is one of the commonly used server is SSH, and they actually also implement a privilege separation. So it's have the privilege and use the privilege mode. So why they does that is basically they have some bug in the privilege process and will compromise the system. And what's important for this research is because some data actually only exists on unprivileged process or vice versa. So this is like the scheme of how it works. So first there's a new SSH connection. It will fork to two child. You have the privilege which will monitor, and then the unprivileged will network processing. And you do the key exchange, authentication. When it's done, it will transfer the state to the privileged one and fork another child for this privilege. So on the right side, if you run it on the Linux server, this is how it look like. So on the right top, it will be during the authentication. You can see in the bracket there is a privilege and there is a network. So the network will handle the network stuff. And then after you finish the authentication, then it will the network one will be joined with the privileged one, and then you have another user privilege. And then you have your shell. For example, this one I use the Z shell. Okay. So this is how the network looks like. So you have payload. The compression is optional. It's not enabled by default. So you press payload, and then you append with the packet length, some padding. Then it encrypted, some text message, and then you append the sequence number. Then you have your MAC data. All right. So what is virtual machine inspection itself? So it's a monitor of machine from hyper point of view. So you have a complete SVM again running as you're running in the hypervisor point of view. Does everything SVM. So there's some actually the monitoring methods available out there for system called tracing. So it's most of the time using by Linux system calls, and then you can trace them what doing by this something like that. For Windows, you have the IP tracing or function tracing, which is what I'm using for this research. And there are some available tools out there that is already easy to use. For example, DMI, volatility with help MIFS. Drugproof and LiveVM Trace is a monitoring library that handmade by us in the University of Basel. It's all available in GitHub. Okay. So to do that, I need to do some breakpoint injection, which is actually similar how it works with software point. So the concept what I can say is with GDB from the outside. I guess GDB is quite common for users as well. So to show you some related work, so there's a SSHKex, which is actually done by my colleague here in Basel. So it tried to force all the memory content onto keys. So it's slow and really a lot of overhead. And then it's being improved. Kex basically trying to follow the pointer without any symbol. So the machine learning assisted will try to predict the structure until you reach the key. And we have the memdecrypt, which is semi-brute-force. It tries to find the data structure that holds the IP and the key, assuming that the IP and the key is closed. Then we have some kind of online. I have another one available online, just called decrypting SSH for profit. So it's quite similar to the third one. Is to find the data structure that holds the key based on the SSH code. You can since it's open source, you can learn the code, and you can look at the structure, and then somehow try to find in the memory that looks like those. So then you can find the key from. So the design of SSHKex. So we have some goals that we are using only passive monitoring. we extract the key from the main memory, and then of course there's some assumption that passive monitoring network monitoring exists, and then we assume that we know which SSH implementation is running on the target server, and the hypervisor itself have PMI capabilities. And the system is x86 base and 64-bit. So this is the overview how does the system looks like. So first it's a setup phase, which is like the SSHKex will activate PMI monitoring. Then you have the network plugin, and it will enable like TCPDump, Wireshark using passive network monitoring. Then you try to capture the trigger, and then when it's new SSH coming, then we extract the key from the main memories. And then the decryption itself from the network packet using standalone Python program that we wrote ourselves, and it's done in parallel, will not interfere with the connection. So I want to go detail about implementation here because I hope that people that interested in this kind of topic can replicate what we're doing here. So if you look at the SSH code, there's a structure and function that's important. So our result is based on OpenSSH version 7.2. So the data structure that is important for us is SSH, which is defined in the packet H. Basically, it's the main structure that all necessary data, like a remote IP, port, session state, and the address. Then we go to the session state itself. Then it contains the data in the particular system or example sync. That's what we're looking for. And there is a new keys that holds all the keys for the encryption and the. And we have the SSH encryption struct, which holds the value of the encryption keys. So the function that are important for us is xDevice. This is accessed in the unprivileged mode. It's called when the generation of keys is about to begin. So we know that there's a new session, and they want to direct the key. Okay. So in this case, we try to hold the address of the SSH. The next one is the new authentication tool, also accessed in privilege. It's called when the key is done. And then they both already using connection. Now the authentication phase begins. So we know that they already encrypted. So now we can extract. So we continue working on this to enhance it. And on the newer version of SSH, we just need to intercept one function, which is the do authentication tool. So from the previous slide, this is like a summary of it. So there's a call from the TCPDump. We hold the address of SSH the RDI registers since it's the first input parameters of the function. Then after the authentication call, we can follow all the pointers until you reach here, which is marked in red. So this my work is quite similar to yesterday's talk, regarding Telegram stop app, which is trying to also read the source code and try to follow the pointers based on the structure or from the source code. Okay. So this is how this looks like for our experimental setup. We are running Z11, and then we have to VM with 200 megabyte RAM and one CPU. Again, we try to improve it further. So in the newer version of SSHKex, it's also running on the KVM. So you can choose KVM or Z. Okay, so result. So this is how it looks like in the newer version, which is now formatted in JSON. I will let you know why in the letter. But then I also log all the process ID of the encryption method name, case I use AES256 counter mode, and then where the key is located, which address in the key, for example. What is the length? What's the actual value of the keys in the hex representation? And it's all for all the keys. So if you recall the one presented in the first time that there's KA until key F. Okay. So we try to have some self-Python to prove that this is actually the key that I've been looking for. So we write some Python script that consume the pcap file from TCPDump and then use the key that we obtained before to try to decrypt the packet. On the left, you will see that's the network packet that we get from TCPDump. Right side is the one that is already processed by the script, and you will get the result of the in plain text. So again, we're not pretty satisfied with that. We prove it even more. Now we also write Golang, which is actually perform master. Then the Python script, but the goal is remain the same. You have the IV, key, and the pcap file that is to decrypt the packet. So on the bottom side, the white one here, you can see the SSH user out. So that's also when it's become when they start the authentication phase. Real that we can decrypt the packet. So to make it nicer for end user that try, we also create Wireshark plugins. This is not the final version yet. So basically you need to import the key that is necessary and then put the cipher name, which port is it, and then it can consume the key to load the key and then try to decrypt the packet. So this is how it looks like. So we have the SSH and filter. You see on the top, you can filter it, and then on the bottom there's we have the frame, which is the decrypted H. And then it is shown that it's already decrypted. You can see the network packet in plain text. Okay, so of course we need some isolation. So we try to measure how the overhead has been introduced by the system. So we try to measure from the client side. Assume that the network problem we are running is at our lab. So we establish scenarios. We establish SSH connection, ES18 counter mode, and accept immediately. And B, when we try to connect it, we also try to clone the repository of the Wireshark. Try to do some load. So in the standard output, we will get some output that being transmitted from the server to the client. And then the C and D similar to A and B respectively, but now using AES256 compatible. So from this graph that I show you, the takeaway is basically it's producing some overhead, but it's really low. The worst case is even not reaching 100 milliseconds. It's quite unnoticeable. So how about the decryption itself with the Python? This is the numbers, packet length, payload length, and time in millisecond. Take away message from this table basically. Of course, the more complicated the decryption mode you use, the longer it takes to decrypt it. You have the AES128 counter mode, AES256 counter mode, and now the latest one we use by default now is HA20 poly. But again, this is done parallel, so it doesn't affect the running system. So why we won't do that? We also try to integrate this into Honeypot or this nowadays is called. So in 2008 we found this basically high integration Honeypot. It extracts the decrypted packet from the memory. The problem is producing a lot of overhead because whenever the packet being encrypted or decrypted, it will be intercepted, extract, and then it zoom the process. So it introduces higher overhead. So if we combine it with SSHKex, we can extract only once, and does the passive network sniffing. That's all. We don't need to intercept the extracted packet anymore from the main port. So I have provided this video demos. Time. Okay, so on the right side, you see the monitoring is running. So it's doing the setup. On the left side is client that try to connect to the server, for example. And then you will see on the right side there the key is being extracted, because again the preliminary version is still lock everything in standard output. Then actually you can extract the decrypted file now. So this is again not really the easiest way, but it works. So we will improve it. We promise that. So we copy the keys from the server, from the monitoring server. Now we have new keys, and then we run now the Wireshark. We import the keys to the protocol. Okay. Now we import the key here, and we give the encryption name and the port. We're now using the counter mode. Okay. So now let's do something to the server itself. Print something. Hello, for example. Okay. Put some even longer string, and then you can see actually on the Wireshark you will get more traffic. Now if we pick one of them, and then you can there's an SSH protocol. And then if you try to decrypt this H, you can see there's an H, for example, A, and then for the longer one, you have L. So like your keystroke is recorded as well, so you know what's type on the server. You have enter button, for example, and for the longer one, like this one, or so it's similar to the one being printed in your standard code. All right. There you go. So it's the same one as that part. Okay. So this is the older version. We also want to introduce the newer version, which is really running smoothly in KVM, and then it will dump everything in JSON format. It's the same. Start monitoring, and then here you can see this the log file now is also in JSON. Again, why? Then I will explain to you. All right. Back to the slide. So some conclusion. So conclusion for me is monitoring network is essential because you can analysis also combined with digital forensic, and the current approach, for example, in the middle or is basic to detect. And here we introduce SSHKex extraction, machine inspection. So extract the key accurately, which is effective with minimum overhead, less than 100 milliseconds, which is called efficient. So the repository is there if you write by yourself. So the future work is basically we want to try machine learning on this. So that's why I put in JSON so it's easier to consume. So for example, we want to get keys from memory dump. So I have a heap of process, then I want to extract whether there's important keys or session keys inside there. So can we also use the same for TLS or the others? So how to build some monitoring for a lab, or even hopefully your proposal presented in DFRWS22. So I will have a paper presentation also there. All right. So that's all from my side. So some time. Thank you. So there are any questions?
Okay, thank you very much for that, Stewart. So one question that I have, Stewart, is regarding the future work that you were looking at with the limitation around having to currently understand the layout of the memory. what's the proposal in terms of trying to address that?
So we want to try the machine learning to learn the pattern. Actually, that's what we want to do as well. So yes, of course, that actually is you can read the source code and you already know about that. So we also need to try to do some randomization there. So, but basically at the end, we want to make some kind the machine learning try to learn the pattern where how keys looks like and where does it should be located.
Okay, thank you very much. Have you any questions from the chat? Okay. Okay.
Thank you very much. That was a really interesting talk. I'm just trying to get my head around the memory inspection part of this project. And I was wondering if you would outline for me what the advantage of doing sort of this live memory inspection is. In essence, why isn't knowledge of the server key from the hypervisor's access to the file system and then the complete network traffic dump sufficient to decrypt the traffic?
So the main goal is actually from the live memory introspection is you can do malware analysis while it's running. So and then yeah, there's some access like a Kuko's inbox, for example, but it's basically proven it's really easy to be detected. So with the VMI, we want to try to make it even more stealthier. So I hope that's answered your questions. And can you repeat your second part?
Yeah, it was just like how would the monitoring of how would somebody detect that the network traffic had been logged and then used for this analysis, given the server key?
Okay, yeah, for that one, I don't have good answer for that because we've done it. Of course, everything is in our lab, which is we can do that. So we assume they cannot detect it, but yeah, now we not yet addressed that part. Yes.
Thank you very much.
Okay, thank you very much, Stewart. That was very interesting.